So today we're going to be looking at how we can apply transformations to integration functions, and we don't actually need to know what the function is for this. So I've whipped up this function here. It's f of x. It's this kind of maximum parabola looking thing. I've got we don't need the actual function for this. We're just going to work in general. I've got the area in blue is the integral between those two x-intercepts that I've got there. And what I'm going to do with this is I'm going to say that this area in blue is equivalent to this rectangle that I've created. The rectangle goes between the two x-intercepts, so between 0 and some other point, and it has a height of a. We don't know exactly what a is, but we do know the height that we have there is a. And I'm just going to color this in a bit so it's a bit easier to see my rectangle that I've got going on here. So I have added in this extra thing 3 times f of x. And you'll be able to see that this 3 times f of x, it still has the same x-intercepts. So we still have the same terminals on our integral. But now the area that we have under this curve, well, it's probably going to increase, right? And what ends up happening with this is that it ends up tripling. If you get 3 times the function, you get 3 times the area. So you can see our rectangle, it's now 3 times as high. We're now going up to 3a for our vertical. The reason that this works, if I whip up the integral of 3 times f of x, that's what our dilation away from the x-axis would look like, dx, and we'll say we're just going between 2 points, don't know what they are, p and q. Well, we have this 3 multiplying at the front, this one that I've underlined here. If you're multiplying an integral by a constant, you can shift that constant that you're multiplying by at the front of the integral, and suddenly we just end up with 3 times our original integral, our original f of x between p and q. So anytime you have the take-home message that we've got for this, if you dilate away from the x-axis, so if you have some constant times f of x is your transformation, in this case I've used a, then you multiply the area by that constant. Dilate away from the x-axis, then you multiply the area by a. All right. Next time, we're going back to our original f of x. This time I've added some terminals on. You can see we've got a terminal on the left at c and a terminal on the right at b. Sorry to all of those of you with mild OCD. We've still got our rectangle in green, and that's telling us, remember, that's telling us an equivalent area to our shape shaded in blue by the area under f of x. What I'm going to do here is I'm going to find f, to make f of 2x, and because the 2 is in next to the x, that's going to be a dilation away from the x-axis. You can see it's made our graph skinnier. And what this has ended up doing is, well, our C terminal, that's more or less at 0, so that one looks the same. But our B terminal, you can see our B terminal has moved further in. If we think about the shape of this, you can see that the height is the same height, but the width of our rectangle, well, that's half as big. If we look at it like this, I've colored it in black for some reason here, we can make a rectangle with half the size, going to b over 2, because we had f of 2x. Take-home message we've got here, if you dilate inside the function, so something like f of bx is what f of x is what we know, and f of bx is what we're being given, then we divide the area by b. So take home a couple of other things. If we have a horizontal translation, so it's something like f of x plus 2, if you imagine moving our rectangle to the left or to the right, that's not going to change the area of the rectangle above the x-axis. So any of those horizontal translations, they don't affect your area. If you have a vertical translation though, then you can split your integral and integrate the two separate parts separately because they're separate. So to give you an idea of what this looks like, we have the integral between 1 and 2 of f of x plus 3 dx. Well, then we can split this up into the integral of between 2 and 1 of f of x dx, which in a typical question you would be given, plus the integral between 1 and 2 of 3 dx, which is something you can work out. You end up with, what is it, like 3x between 2 and 1, so 6 minus 3 is 3. And you've still got this integral between 2 and 1 of f of x dx hanging about. And I'm going to do quotation marks because I'm lazy. A quick note with this, it can take a lot of brain power to think about the terminals for these, but every time I've ever seen this pop up in a VCAR exam, the terminals have been worked out already for you. My strongest piece of advice to you when you're doing these problems, don't worry about the terminals on these integrations, except for when you've got something to figure out yourself, like this between 2 and 1 of 3 dx. If you have something like the integral between 0 and 4 of 4 f of x, let's say, or f of 2x minus 1, if you've got something like this, and it's asking you to figure out the integral of f of x between 0 and, I don't know, 18, something like that. Whatever it is, don't worry about these terminals being different. Don't worry about the 18 and the 4 being different, because VCAR or whoever is setting the question has set it up so that it is the same for you. You don't need to worry about that. All right. Good luck, everybody. Bye-bye.